I want to invite Michal from Nethermind to talk about the difference between security proof of SNARK and their actual applicability, right? I'm getting it right?
Yeah.
Yeah? Okay. So, Michal from Nethermind.
Okay, does it work? Okay, I think it does. Perfect. Okay, yes. So, hello, my name is Michal. I'm head of research at Nethermind. And today I would like to talk about the security difference between what we see in a scientific paper and the protocol that actually we get to deployment. So there are some steps in preparing the protocol for practical deployment that actually reduces the protocol's security, and that's what I would like to discuss today to make you maybe more aware of some caveats of security analysis. Okay, so let's start with like super basic primer and on zero knowledge, and let me introduce some notation. So in zero knowledge proofs, we have these two parties, prover, verifier. Prover gets some statement X that that belongs to some language L and wants to convince other party, verifier, that that's true, that X indeed belongs to the language. Verifier knows X itself, but does not know the additional information W, called the witness, that certifies that X indeed belongs to the language. So, for example, X could be some statement like circuit C executed on input A gives B, and W could be some private information included in the circuit. And we have a number of properties that we require for a proof system to have. We have completeness that tells that honest verifier always accepts a proof from an honest prover. We have soundness, which is much more interesting property, which tells that dishonest prover, and during this presentation I will use this P star notation to denote provers that are dishonest. So dishonest prover should not be able to convince the verifier to accept some false statement except with some negligible probability. We have a stronger notion, knowledge soundness, that basically states that if the prover was able to convince the verifier on the veracity of some statement, then prover knows the witness corresponding to the statement. And finally, we have zero knowledge, which basically tells that the verifier learns nothing about the witness except, the verifier learns nothing new except the veracity of X. Okay, so now, how SNARKs are built. So usually SNARKs are built in a quite similar manner. So everything starts with PIOPs. PIOP stands for Polynomial Interactive Oracle Proof. And this is idealized model that is super easy to analyze because of the very nice algebraic properties. So here we introduce like magical third party, which is an oracle. And prover sends its proof as polynomials sent to the oracle. So prover does not communicate directly with the verifier. It sends some polynomials to the oracle, gets some challenges back from the verifier, and replies with even more polynomials. And at the end of the day, the verifier picks some evaluation challenges, here Z, and asks the oracle to get polynomial evaluations at Z. And then with that polynomial evaluation, it decides whether to accept or reject the proof. So the oracle always like this magical party that always tells truth here. The biggest problem with this is like we don't have such oracles in real life. And the second is that these proofs are really huge. So if you have like a computation of size 2 to the 20, then these polynomials also are expected to have like 2 to the 20, say, field elements. So the polynomials are of the size of the computation. So how we get rid of the oracle? We use polynomial commitment schemes instead of polynomials themselves, right? So instead of sending polynomial, we send a commitment to a polynomial, like very short digest. And at the end of this conversation between prover and verifier, when the verifier sends the evaluation challenge to the prover, prover replies with evaluation along with proof that the evaluation was computed correctly. So now the problem that remains is that this protocol is interactive. And this is an issue because we don't want to deploy in practice interactive protocols, right? When you have your favorite ZK rollup, you don't want to talk with say, Ethereum to get the challenges from there. You just want to post the proof and be done. So what you do Fatam transformation, where you basically replace verifier's challenges by random oracles. So you send information, partial transcripts of your conversation to this idealized third party, random oracle, and get random challenges from there. And this, importantly, these transcripts needs to be computed in a quite carefully because there are some vulnerabilities that come when you do when you don't include some information in these queries. Finally, random oracles don't exist. So instead of using random oracle, we use hash function, right? So now here the prover computes all the challenges himself by making queries to some random oracle, by computing the challenges as evaluations of a hash function. Okay, so there's a number of questions that come when we go from PIOP to concrete SNARK. So first of all, our first step introduce polynomial commitments. All right, so we need to analyze like how secure the polynomial commitments are. Like, do they have all the properties we need? What's the security laws that come with using polynomial commitment instead of this idealized third party, the oracle? Now, we replaced the interaction with random oracles. So the question is whether this introduces some new attack vectors. And this will be the main topic of my talk. Finally, we replace the random oracle with hash function. And so the question is like how good the replacement is. Okay, so let's get into Fatam transformation security. So on the left-hand side, we have an interactive protocol where a malicious prover tries to convince a verifier about veracity of some false statement. On the right-hand side, we have the same protocol, but with Fatam transformation applied. And the intuition why Fatam transformation introduces some security loss is following. If I'm a malicious prover and I talk with verifier, when I cannot reply to some challenge, that's the expected result because I don't know the witness. The statement does not belong to a language. When I cannot reply some challenge, the only thing I can do, I can start from the beginning of the protocol, right? Because otherwise the verifier will just reject. On the other hand, if I have a hash function and I compute challenges on my own, then when I see a challenge that doesn't fit my needs, that I don't like, I can always get back some points in the protocol, change something in my proof, like re-randomize the proof, for example, and try again, such that I have a new challenge with every query. And in that way, I have bigger chances of getting challenges that fit my needs, that would make the verifier accept. So here, let me introduce lucky set and lucky states. So lucky set is a set of challenges sent by the verifier, such that if I, as a malicious prover, get a challenge from that particular set, then I know how to make this conversation further on, such that the verifier accepts. Okay? And I say that at this moment, when I get the challenge from lucky set, the protocol gets into lucky state. And the verifier accepts only if the protocol at the very end of the conversation is in the lucky state. So to introduce some notation, let's have epsilon, the probability that P star makes V accept a false statement. Eta will be the probability that pi gets into the lucky state in a single round. So the probability that during k rounds, pi doesn't get into the lucky state is 1 minus eta to the k, like the interactive case. So finally, we can express our epsilon as 1 minus eta to the k, which is roughly k times eta. So this is without rewinding, right? This is the interactive case. So okay, so let's go into rewinding. Let's see what happens when we allow adversary to rewind and to check like new possibilities. So here I will also introduce Q. So Q will be attacking budget. So basically it will tell like how many times I can try to rewind. So okay, again, 1 minus eta is a probability that P star does not get a challenge from a lucky set in a single round. Then we have rewinding. So I divide my budget for rewinding as follows. I have Q budget. I have K rounds. So in each round, I'm willing to spend like Q by K. I'm willing to do like Q by K rewinding, right? So this probability that I'm not getting into lucky set drops to 1 minus eta to Q by K. Finally, I have K rounds. So I multiply. So I have product from I equals 1 to K of 1 minus eta Q to the Q by K. Okay, so the security of this Fiat-Shamir transformation is actually much worse because it's eta times Q. Previously, we had eta times K. So the question is, like, how big is Q? So let's take, as an example, epsilon equals 2 to the minus 100, okay? So this is the security of our interactive protocol. So it looks pretty decent, okay? But then let's say that we utilize the Fiat-Shamir transformation. So what's the Q? As an illustrative example, let's look at Bitcoin network, at how many hashes it can compute. And then let's use the number of hashes that are computed by Bitcoin network as our measure of how many rewinds the adversary can make. And this is, of course, like computing hashes is a bit different task than what we are asking for, but there are some big similarities because, well, when I rewind, I basically what I do is that I have some message that I send to the verifier. I randomize the message, and I compute the challenge that comes from randomization of this message. And that's very similar to what Bitcoin miners do. They need to find the nonce such that if I add this nonce to a Bitcoin block, the hash of that block has certain properties, right? So there is a lot of similarities here. So with Bitcoin network being able to process 60 million terahashes per second, they process around like 2 to the 85 hashes per day. So with our formula, we get that epsilon is like 2 to the minus 100 times q, and this is like 2 to the minus 15, right? So that's our probability that during a single day, our protocol will be broken. So the security difference actually here, when the Fatam transformation got applied, is huge. Okay, so we can do better. So we can actually bootstrap the security of our protocols by utilizing parallel repetition. Okay, so parallel repetition, as name suggests, means that my protocol is repeated in a parallel fashion. So the prover now gets into interaction with verifier in like two protocols, and it needs to convince the verifier on both of during both of the interactions. And here, when we have interactive proof, and the security of the interactive proof was epsilon, then when I have parallel repetition of two protocols, then the security is epsilon squared, right? So this security loss drops significantly. We would love to have the similar if we use Fatam transformation. Unfortunately, that's not the case. The security drop is even more significant here. Okay, so let's get back to our lucky sets. So we denote by B the lucky set for the challenges. I assume that all challenges come from the same set N. By eta, I denote the maximal probability that the protocol enters a lucky state. I have K a number of protocol rounds, and T is number of parallel repetitions. Okay, so when I have that's an interactive case, right? For a bigger number of executions. So in the interactive setting, when I have bigger number of executions, the security actually grows to eta times k to the k. And for some concrete example, let's set t equals 8, k equals 4, eta equals 2 to the minus 20. So if I have a protocol that is secure with eta equals 2 to the minus 20, so it's like really not a secure protocol, right? Then after repeating in parallel 8 times, I get the security of 2 to the minus 144, which is significantly better. So for Fatam transformation, actually that's not the case, and let me explain why. So now I will be dividing my attacking budget into these 2 runs of the protocols, and my strategy will be as follows. So the prover will send the first message, okay? We'll get some challenge B1, and if this challenge doesn't belong to a lucky set, then I will rewind, okay? And I will repeat this procedure up to q by 2 times till I get B1 that belongs to the lucky set. Okay, and then what I can do is that I say freeze the first transcripts in both of the protocols. So here, the transcripts actually depends on each other, right? So the transcript 1 on the left-hand side is the instance and the first prover's message. And transcript 1 on the right-hand side is actually what the prover got from, it's the transcript from the left-hand side with some additional information like identifier that it's the second interaction, for example. The challenge I got, say I spend this budget Q over 2 to get like a good challenge from the lucky set. And then I compute the second challenge, and this second challenge, B1 on the right-hand side, contains all the information that was exchanged before. So it contains tier 1 from the left-hand side, tier 1 from the right-hand side, and also B1 from the left-hand side. And what I do is that I get this challenge. I send transcript 2 in the first round, in the second round. In the first round, I'm already in the lucky state, so I don't need to care about anything here. And in the second, I'm still not in the lucky set. But what I can do, I can take the challenge B2, and if I don't like it, I can rewind to get a new transcript tier 2, what also would give me a new challenge B2. Okay? So the power of this attack comes from the fact that I can solve the first instance, then get into solving the second instance, and somehow solve them independently, breaking this parallel repetition problem. Okay, so let's analyze the lucky sets in the Fiat-Shamir transformation. So similarly, we have yes, so we have 1 minus eta, the probability that I'm not getting into a lucky set in a single query. Then I need to get it to the q by t power, because that's how many trials I'm willing to make. And then I take 1 minus eta to q by t to express the probability that I'm not going to, sorry, the probability that I'm entering lucky set in this first iteration, the first track of the protocol, right? And I have t iteration, so the end result is q by t times eta to t. So for a concrete example, when I have t equals 10, sorry, it should be t equal 8 actually, and k is equal 2, and q is 2 to the 20, eta is also like 2 to the minus 20. So q here is like really small, but the end result is 2 to the minus 30. So the security dropped from 2 to the minus 44 to the minus 144 to 2 to the minus 30. And actually, there is more caveats when we use Fiat-Shamir transformation to implement our protocols. So there's a result by Trail of Bits, also mentioned this morning by Benny Pincus. So what Trail of Bit realized is that a big number of cryptographic protocols that were used in Web3 don't have Fiat-Shamir transformation implemented correctly. So there were information that were missing in the transcripts that allowed researchers from Trail of Bits to actually break them. And we have like some good examples here. We have like ENG Bank, we have Dusk Network, IDEN-free consensus. So TLDR is that some implementations of Fiat-Shamir transformation include all the necessary information in the hash function. And one more attack that was very recently published by researchers from OpenZeppelin is they realized that some implementations of Plonk, which is a very, very popular SNARK proof system, don't compute the challenges correctly, meaning they don't pick the challenges from the right set. And that also allowed the researchers to break these protocols. So the conclusion of this talk is be careful when you fine-tune your parameters. When you cannot only look at the security parameters for your interactive protocol, you need to account for all the changes you make in your protocol to see the concrete security of the protocol at the end of the day. Thank you.
Thank you very much, Michal. Yeah, question.
What did ING Bank use ZK for?
That's a very good question. I have no idea. But to be honest, I'm quite happy to see that name that they are using ZK, right? Even though they don't use it properly.
Anyone else? Great. Thank you so much, Michal.